what can we do to build more secure systems? Of course, the research literature, researchers, and many people in this room have tried to come up with lots of different answers for this question over the years. But here, I would like to focus our attention on one particular class of mechanisms for improving security: reference monitors. So the idea is conceptually very simple. We have some system that is running some computation. To make it more secure, we're going to add a new component into the mix, the monitor, which is going to inspect each action that our system tries to perform to decide whether it's safe or not. So it's usually going to allow our system to do its thing, but it might be the case that it detects that the system is about to do something dangerous, in which case it will just intervene to prevent greater harm from happening. Reference monitors are great. They have many benefits, but they do suffer from one pesky problem. And this problem is that they're usually very slow. Now, this often happens because these monitors are implemented in software, which has led some researchers to wonder, well, maybe we can make these things faster by adding some hardware support for them, right? So now our picture looks like this. Instead of having an extra layer of software to implement our monitor, we'll have it programmed directly into the hardware. And because our system does not suffer from the extra software overhead anymore, it can do much more than what it used to be able to with a software monitor. So this is great, but now we run into another drawback, which is that hardware is much harder to redesign and redeploy than software. So if we come up with special hardware support for a particular monitor that is hardwired into our system, we may have adequate support for defending ourselves against a particular class of threats, but tomorrow, a new class of attacks will show up and will render our mechanism useless, right? So this is not very good. This scenario is what motivated us to work on this idea of micropolicies that I'm here to tell you about today. So micropolicies are a programming model for reference monitors that is designed to be flexible and capable of delivering concrete security guarantees, but that can also be efficiently executed with some special hardware support. Here in this paper, we present this micropolicy programming model and evaluate it under the 3 design goals that I just laid out. So to demonstrate that the mechanism is flexible, we show how we can use it to program a diverse set of 4 policies that have received attention in the research literature. Once we do this, you might ask yourself, but wait a second, you just introduced this programming model, you programmed all of these policies. How do you know that you got these policies right? How do you know how they're improving the security of your system? Well, to answer this question, we formalize the micropolicy programming model using the Coq proof assistant, and then use this formalization to elaborate micropolicy specifications for each of the micropolicies that we implemented, connecting one to the other via a machine-checked proof. This machine-checked proof ensures that each micropolicy implementation is capable of delivering the security guarantees embodied in the corresponding specification. As for the last design goal, performance, we present a formal model of a hardware extension that is designed to accelerate this programming model, which we call the pump, for a programmable unit for metadata processing. And although we do not evaluate the performance of the pump in this paper, I should let you know that we have many collaborators working in improving the design of the pump and testing it on benchmarks. So if you're interested in learning more about microarchitecture details, simulations, and performance figures, I can refer to a recent S+ 2015 paper where we showed that micropolicies can be accelerated using the pump and executed with a runtime overhead of less than 10%. So what exactly is this programming model that I've been talking about? Well, when you're programming reference monitors, generally, you can allow yourself to inspect the program state in arbitrary ways, right? This is good because it means that there's lots of things that we can implement using reference monitors, but it does mean that if we're trying to come up with efficient hardware support for it, this will be much harder because the model is just too general. So with micropolicies, we'll be willing to trade in some expressive power to make our lives easier when efficiently supporting these things in hardware. And the way micropolicies work is with this idea of computing on metadata associated with the program that we're monitoring. Now let me explain what I mean by this. So suppose that you have a processor that has some internal state, it has a set of registers, it has a memory with a program that is running, and a program counter. So in the micropolicies world, each piece of data in the system is going to be enriched with a metadata tag that describes this piece of data somehow. As far as the user-level code is concerned, this tag is indivisible from the corresponding payload part. So the user-level code cannot separately address these tags, cannot inspect them in any way. The only part of the system that is allowed to interact with these tags directly is our monitor. And this monitor is supplied by a policy designer as a piece of code that is going to analyze these tags in some way. And it's up to the monitor effectively to decide what these tags mean. I should emphasize here that when doing so, we give designers lots of freedom to decide what these tags mean, because at the implementation level, these tags are actually pointer-sized words, which mean that they can be used to reference arbitrarily complex data structures in memory, for instance. So what does this monitor do? Well, suppose that we try to execute some instruction in our program. For instance, we could be trying to add 2 registers, R1 and R2, and put the result in R3. Our monitor is going to look at the tags that are related to this particular instruction. So it's going to analyze the tag on the program counter, it's going to look at the tag on the current instruction that we're executing, and it's going to look at all the tags of the arguments that this instruction might take. And solely based on this information, it's going to decide what to do. So it could be the case, for instance, that our monitor allows this operation to happen, in which case it will produce a set of tags to be used on the results of this instruction. So we'll have a new program counter in the next cycle, so we'll update the tag on the program counter, and we just stored a new value on R3, the result of our sum. So we're going to update the tag of that too. But again, it could also be the case that upon inspecting these tags, our monitor decides that we're about to do something dangerous, and it prevents this dangerous thing from happening. So now that we have a high-level idea of how this programming model works, let's turn our attention to our design goals. First thing that we wanted to know is this thing actually flexible? Well, to answer this question, in this paper, we show how we can use this mechanism to implement a diverse set of 4 interesting policies. So we have a micropolicies implementation for doing control flow integrity. We have a micropolicy implementation for doing software compartmentalization, inspired by Wabi's model on software fault isolation. We have a micropolicy for doing memory safety of dynamically allocated heap regions, and also a memory safety for doing dynamic sealing. And because we're able to implement all of those with a micropolicies mechanism, this leaves us very confident in how flexible this mechanism is. To give you an idea of how this works, let's consider how we can use this to implement a micropolicy, control flow integrity. So the first observation that we have is that because we have these tags in memory, we're already able to differentiate code from data. So assume that I have some trusted loader that upon loading the program is able to mark all the words in memory that correspond to the code of our program as code, and everything else as data. And because our monitor has this information available, it can already implement some interesting policies on that. So for instance, if our monitor sees that the current tag on the instruction is data, it's going to halt the program because this means that we're trying to execute data which shouldn't be allowed. And we could also stipulate that when trying to store to a memory location that is marked as code, we're also going to halt the process because we shouldn't be allowed to overwrite code. But because these tags can be arbitrarily rich, we can do much more than this, right? So suppose that I have some control flow graph for this program that we're executing. It could be, for instance, the result of the compiler that produced the binary for the program. What we do with that is that we're going to take node identifiers that correspond to each node in this control flow graph, and we're going to associate these nodes to the tags in our instructions. Additionally, we're going to mark the program counter with the identifier of the last instruction that we executed. Because once we do this, our monitor has all the information it needs to see which edge in this control flow graph we're trying to traverse. So for instance, if our monitor detects that the current PC tag is 4 and that the current instruction tag is code 5, this means, according to our convention, that we're trying to go from 4 to 5 And this is OK, because it is in our control flow graph. But if we try to do something else, as the result of some programming error or some attack, like going from 1 to 5, our monitor will be able to say that this is not OK, because this is not part of the control flow graph. So good. We've answered the question of flexibility. But now we have these policies that are implemented with these tag analysis. And how do we know that they are correct? How do we know how they're improving the security of our system? Well, as I mentioned before, we're going to use this interesting tool called the Coq Proof Assistant, which, if you're not familiar with, you can think of as being a programming language for mathematics. So you can use it to write down precise mathematical definitions and prove things about them. In this paper, we use the programming language to define what the micropolicy programming model is. So our definition looks like this. We start by defining a simplified RISC processor whose features are supposed to be representative of common RISC processors that you find out there in the market, like a MIPS or an Alpha, for instance. And then we're going to enrich the data pieces of this processor with tags and a monitor that are defined by the user, the micropolicy designer, which work as I explained before. When supplying these tags, the policy designer is going to use arbitrary Coq programs, which are written in this very high-level functional programming language. And this is good because it gives the policy designer a lot of freedom to describe their policy and reason about them. So for instance, on the screen, there is an excerpt of a piece of code that you could use to implement a simplified version of the control flow integrity micropolicies that I just mentioned, where you define a data type of tags to be used in memory, along with a function operating on those tags to decide whether a given machine step is allowed or not. And once we have these policies implemented, we can turn our attention to their specifications, right? These specifications are ultimately going to give our threat model for this system. So in our model, we typically consider that the attacker controls the input to our system, but does not have any physical access to the machine where the program is running. I should also let you know that there are a few things that we don't model in this formalization. So we don't, for instance, consider erratic DMA controllers. We don't consider timing issues. But anything else that fits within this model, you can reason about and formulate as a micropolicy specification to figure out what your policy is buying you in terms of security. So what do we do in this paper? Well, we usually consider specifications of this form. We elaborate a higher-level abstract machine that is supposed to embody a more structured programming model than just bare-bones assembly programming. And then we show that this higher-level machine can be implemented by particular micropolicies. So for instance, I mentioned that we have this micropolicy for doing memory safety. We could implement an abstract machine where pointers and integers are not interchangeable. They're different data types. And a pointer can only be used to access a certain region of memory that it has the capability for. If we go off bounds and try to access some other region of memory, our machine will be able to detect this and prevent an attack from happening. And then we're able to show that this abstract machine that is more structured than just assembly programming is indeed implemented by our memory safety micropolicy. We could also consider other forms of specification. So for instance, for our control flow integrity micropolicy, we're able to show that it gives similar security guarantees than those given by a body's CFI property, which roughly states that a program is always going to execute within its control flow graph, even in the presence of an attacker that is able to change data bits in arbitrary ways, non-deterministically. So that's it for security. What I wanted you to take away from this endeavor is that with a little bit of careful design, we can come up with a programming model for writing expressive high-level policies for security of low-level code. And because this model is based on a model for hardware acceleration, we can do this with reasonable overheads. Needless to say, in this talk, I've only mentioned the tip of the iceberg of the work that we've done in this paper. So if you're interested in learning more about it, such as details of the micropolicies we've implemented, of the programming model, of the formal proofs, you can have a look at the paper to learn more about this. You'll also find there a description of the formal model of this hardware extension, the pump, that we use to accelerate these micropolicies, as well as a proof that the pump can be used in a way that cannot be circumvented by the user. So the pump itself is capable of enforcing its own protection. All of our source code is available on GitHub if you want to have a look at it, or maybe build some micropolicies of your own and prove them correct. I would like to conclude my talk with a few things we've been working on. So we've been considering how to implement more policies with this mechanism in some use cases. In particular, we would like to see how we can use the compartmentalization micropolicy that we've developed to build an operating system that is compartmentalized. We'd like to develop a theory of policy composition that would allow users to combine different policies and the guarantees that are proven about these policies. And we'd also like to improve the guarantees that we get from this formal model. By scaling our processor model at Rio ISA, that's what's actually going to be deployed, and be able to verify actual machine code implementations of the policies that we have, connecting them to their more higher level model to get all the guarantees down to the machine code level. And that concludes my talk. Thank you very much.
We have lots of time for questions. So you showed me that your based on risk model. Say
yes.
that I should want to use this on x86. What part of the proof I can reuse from your platform?
Let's see. So I think the harder part would be adapting the lower level layer, because there's a lot of assumptions that we have there that are specific to risk. For instance, working with fixed width instructions. But beyond that point, we actually have a refinement proof that shows that there's a, so to speak, higher level programming model that can be implemented by this machine. So if we were able to use something more x86 like at the bottom layer and still build a refinement proof, you would be able to use all the specification proofs that you have for the older policies.
Hello, Sam Weber at SEI. So you said that your technique was going to be very fast, and sometimes your takes could be pointers to complex data structures.
Yes.
I would imagine that the more complex operations you do on data structures,
yes,
there'll be a high performance impact.
Indeed. So we're still exploring the performance characteristics of the pump. We know that it works well for a given set of policies, but we obviously have no way of knowing how well it performs on more complicated policies. So presumably, there will still be some work involved, some creativity involved in coming up with efficient policies, even in the presence of this hardware acceleration.
Okay, so if you still limit your policies to things that require just one level of indirection, are you still fast?
Well, we don't have a clear answer for that yet. We do have policies that use data structures in memory, and those seem to perform well. But if you start to build arbitrarily complex data structures, then maybe you're secure, but maybe not as fast. Yes?
It's important to recognize that the fast path, where you hit in the cache, doesn't involve following any indirections. So in the fast case, you're just looking at the pointer, which is what's stored in the tag, and manipulating those. Only when you miss in the cache do you have to follow pointers and examine memory structures.
So I probably further come on to that. The interesting question there, of course, would be what the working set for that cache is and what you do in terms of policies that cause an overflow. But my actual question has to do with the composition of policies.
Yes.
Is it the composition of the policies you've explored always coherent? Does it ever run you into situations where you lose security properties you want or you lose program functional properties you want?
Well, that's exactly what makes composition hard.
I agree.
So there's always a naive way in which you can compose the policies, which is you just combine all the tags together in a big tuple, and you try to enforce those simultaneously. But maybe, for instance, if you try to combine, say, information flow control with a memory safety policy, then the information flow bits might, sorry, the memory safety bits might interfere with the information flow control bits, and then you might lose some guarantees. So it's important to figure out how to combine these policies, and right now it doesn't seem very trivial.
Yeah, I mean, there's a lot of experience showing that arbitrarily atom smashing policies lead to fail open problems in security, and it would be nice to, as part of your proofs about this, prove that the compositions have overall properties you want, if only we knew what they were. Yeah. And do you anticipate that software would ever hit cases when it would violate the policies you describe in a non-exploit situation, or is it really you anticipate people write software, they maybe prove or otherwise reason about some properties of it, it runs, and you never hit the exception case where the policy fails?
I'm sorry, can you repeat the question, please?
So, I mean, you can just, if you have a set of constraining policies such as information flow and CFI and so on, you might ideally think to yourself, if this is exploit mitigation, then in normal operation, you would never violate any of these policies, and therefore your software would run as though the policies weren't being enforced in hardware, which is to say, you know, they are enforced, but nothing changes the software control flow or fail stops the system. But if you're exploited, then you might fail stop or have some exceptional case. Do you envision that there would ever be exceptional cases and failures that might happen in normal operation, or is this really just kind of a seatbelt, and then when something goes wrong, the seatbelt suddenly stops the behavior that you're uninterested in?
So I'm not sure I understand the question very well yet. Maybe we can take this offline.
Sure. Okay.
Exact speaker again?
Oh, you can. Please jump in.